Hello, class. Um, this video should hopefully not have too many cats trying to get in the room, and it will be uh, going over some stuff that the other videos may not have covered, going over types of forces and things that you have seen. This slide is the equations that you may expect to see in some places, and then we'll go over the types of forces and how to deal with them. There's other types that you're not going to see, but not going to see equations for, but you'll have to know how to deal with them. And so we'll go over them, and then how to solve problems in general. In future videos, stuff I'm going to make tonight, you'll have going over particular things that's come up in the homeworks, so you at least have uh, some review of that material. You'll have these slides tomorrow, hopefully. Uh, hopefully I get them actually attached to the email. All right. So, just a little bit of review. The other sorts of slides and the other videos will talk about Newton's second law, which is saying that if you add up all the forces acting on an object, that sum of all the forces is going to equal the mass times the acceleration. All right, so our goal is usually to find the acceleration vector so we can do kinematics. And that means we can find it in terms of components. And it doesn't have to be x and y. It can be perpendicular and parallel to something, or into a circle and tangent to the circle. As you've seen in the circular motion stuff, we talked about the tangential and radial accelerations. We can identify forces the same way. The idea is that when we split a vector into components, the components do not interact with each other. And so that happens here. All the forces that have in the x direction, those x direction components add up separately to give you the mass times the acceleration in the x direction. And then in the y direction, the same thing, mass times acceleration in the y direction. So you can split. You don't have to do vector math by drawing. You can do it through components. And so it's going to be a lot of doing vector math. And then I'm going to introduce the rest of these formulas in the next slides. Particular, the weight force or the gravitational force is always going to be toward the Earth, straight down, or it's going to be toward the center of the object that's doing the gravitational force, the attracting object. And the idea is that on Earth, it's very straightforward. The weight of some object caused by the Earth, right? Where in this case, this notation is on an object by an object, and so it's a little backwards, but that's just going to be the mass times this gravitational acceleration. That force is always going to be straight down, so you can just find the length of this. It'll be a number, and you know that it is in the minus y direction. It's straight down, straight towards the center of the Earth. If it's between objects, then there's this longer way of calculating what that force is. You'll see this in chapter 12, so it'll be in about 8 weeks that we'll go over this. All right. So in the lab activity, we introduced the idea of normal forces, and that gave a little concern, and I'm going to go over that in a video. But the idea of normal forces is that they are always perpendicular to some surface. That surface can be in any direction, but if there's a normal force, it has to be perpendicular to it. And the idea is that normal forces, think of them as supporting an object. They prevent acceleration in that perpendicular direction. And so if there's a normal force, you do not expect the acceleration to be non-zero. You expect in the direction of a normal force, the acceleration should be zero, that makes an assumption here. And that assumption is that the object providing the normal force isn't accelerating as well. You could think of something like being in an elevator. When the elevator starts moving, it's accelerating, but you still feel a normal force in the elevator. And that's because the entire thing is accelerating. And we'll talk about how to deal with accelerating frames of reference. But for now, you can treat it as if you see a normal force, you don't expect the object to move relative to that surface. Then we have tension forces. All right, this is the page of everything that doesn't have a good formula for it. Tension forces are going to be forces carried or mediated by ropes, strings, cables, tendons, ligaments. If you grab someone by the arm and pull them up, then there's a tension force in your arm and their arm. If you hand them a tree branch to pull them up with, that tree branch has a tension force in it. Tension forces are pulling forces. Right? And if we wanted to divide these, normal forces are pushing forces. Tension forces are pulling forces. And so tension forces are transmitted through a material, and the tension is the same at both ends of the material. That's kind of the key thing. If there's going to be a formula, you're going to relate the tension at one end of a rope or a cable or a ligament or whatever it is. You're going to relate it to the tension at the other end, which will generally be connecting two objects in some way. So when you see normal forces and tension forces, you just think of two objects that are in some way connected or interacting with each other. Friction force is the third example of things interacting. Friction forces are always going to be along some surface, and they're always going to oppose the motion of the object. So if you can identify a velocity, the friction force will be opposite that velocity vector. If there is no velocity vector, you may have to estimate which way the thing should try to move, and then the friction force is in the opposite direction. Friction forces always try to prevent the motion of the object. There is what's called the coefficient of friction, which will have a nice relationship between normal force and the friction force, but it depends on the material makeup. So it's the sort of thing you have to look up for a pair of materials or calculate it. And often we will tell you what it is or ask you to determine it from the problem. If things are not moving, the friction force is only what it needs to be to make the net force zero. Because if a thing's not moving, it's not accelerating. But it's limited. The friction force has to be less than this coefficient times the normal force. And so there's two coefficients. There's one for it not moving and one for it moving. So the not moving is called the static coefficient of friction, mu sub s. If it's just about to move, then this is an equality. The net force is zero, and this friction force is mu sub s times the normal force. And finally, if it's moving, there's a new coefficient, which is generally a little bit lower, and the friction force is mu sub k times the normal force. And this is absolute equality. You can have, once the object's moving, it can accelerate. It may not, but it can accelerate. And this formula will give you the friction force regardless. So if we're solving problems, we need to go through a certain process which has a lot to do with the process for kinematics. So you're going to want to make a better drawing, something that can include all the information. And in particular, you're going to make a free body diagram. A free body diagram is a way of organizing the forces so that you can sort of see what's going on. In a sense, you can know what forces are acting on an object, what directions they're in. If you wanted to, you could graphically move them around and see where the net force needs to point to. All right, so you could, in principle, graphically add these up and come up with the net force. But a free body diagram only has force. It's only the forces on the object, and it's got to be labeled correctly and consistently so that you know what's going on. Then once you make this free body diagram, and we'll practice it, you're going to want to choose some coordinate directions, and you don't necessarily want X and Y. That is an option, but oftentimes you have an idea of which way an object's going to move. Right? If I describe a problem that is a car rolls down a hill, you would like for the acceleration to point down the hill, parallel to the hill, along the direction of motion, and perpendicular as your coordinates directions, as your axes. Or you want to pick along surfaces. Right? Maybe you have an object that's just sitting on a ramp. It's not moving, but it makes it so much easier a lot of the time to pick parallel and perpendicular to a surface. Or you can pick the X and Y directions. The idea is that the forces have to add up as vectors. It doesn't matter what your coordinates are, you will get the same answer. The reason for picking particular ones is to pick easy ones to work with. Once you pick your coordinates, then you want to find, if you have something that has components, you want to find those components. Most of the time you're trying to pick directions so that most of the vectors are only in one coordinate direction. They're in the X direction or in the Y direction, or they're perpendicular or parallel to some coordinate direction. And so you're trying to minimize the number of vectors that you're trying to find components for. So once you've done this, once you've picked your directions and found components, you're going to add up the components of the forces, which is applying Newton's second law. You're finding the sum of the forces, and if vector components are going in the direction, you subtract them. And you possibly also list other forces that you know, right? Right. Generally, what you do is you say what the weight force is, and then you may have to go and say, well, the weight force is the mass times g. Right? Maybe you're trying to find some other thing. All right. And so, if you know that tension forces are equal at both ends of the thing transmitting the tension, the cable, the ligament, the tree branch, whatever it is, if you know that those forces are equal, you can state that. And if you know that if you've drawn two free body diagrams and you've identified third law pairs, then you would identify those. And if you know that there's a friction force, say you know the object's moving, then you know that the friction is mu sub k times the normal force. And you know that if there's a friction force, there's a normal force. So you know that there's a relationship between them. All right. So you list a bunch of things that you know so that you can eventually solve for the things you don't know. And then you have to sort of think, how am I going to solve the problem? And there's generally two types of problems. There's an equilibrium problem, which means that your acceleration is zero. Usually it's things not moving, but it's generally constant velocity. The forces are balanced. The sum of the forces is zero, but you're trying to find some unknown force. Okay. And then the other sort is non-equilibrium, which is the object is accelerating. So you may not know the acceleration, and the goal may be to find the acceleration. Or you might know what it is, and you're trying to find an unknown force. But depending on which group your problem falls in, whether the acceleration is zero or non-zero, whether it's equilibrium or non-equilibrium, it's going to tell you how to set up Newton's second law for each problem. And then you'll see hopefully from that how to pursue solving the problem. Okay. So the next few slides in these notes are problems to go through. All right, one is a tension problem. One is a kinematics problem where you need to find the frictional force to figure out how the sled is coming to a stop. And one is where you have two objects, and so you'll have a normal force between them, and you'll have third law forces. The idea is to figure out what the acceleration is eventually. So the idea is to go through these problems at some point. This may not occur in these videos. It may occur Monday or at a later time. But all right, the goal for this was to introduce the sort of problems you're likely to see, the sort of problems you need to solve, and the sorts of forces that you're likely to see in problems. And of course, the previous notes also talked about other distinctions between forces. This is all talking about playground physics. We're not talking about electricity and magnetism. We're not talking about gravity over long distances. We're talking about stuff that you could experience in principle. So, we're going to go through those sorts of problems, and we will expand outwards as we need to. All right, so that should conclude this video. We're going to go through and do practice problems and go through some of the things that you had difficulty with over the last week, and we'll see how that works.